Our next speaker, if y'all were here earlier this afternoon, thank you, Adam. We heard a lot about data and collecting data, and our next speaker is going to talk to us on some of the methods to collect some of that data using transducers and telemetry. We have with us Raymond Straub, who's a professional geoscientist with Straub Corporation. He's a second-generation groundwater professional. He's also a board member with the Permian Basin Underground Water Conservation District. Please welcome to the stage Raymond Straub. So forward, backwards, and the little red line is your laser.
Thank you for having me.
Yes, sir. Thank you. So I'll kind of keep the clock down there if you happen to see.
Good afternoon, everybody. As he said, my name is Raymond Straub. I'm a professional scientist. Can I see anybody raise their hand who deals in groundwater? Good showing. How about people that deal with transducers? Well, pretty good showing. Who's ever had a problem with transducers? So we'll talk a little bit about understanding these magical instruments that cause us so much trouble. If you could see it, they would call it surface water, right? But you can't see it. It's below ground. You have to work really hard to understand it. There's only a few ways of actually understanding and locating and measuring groundwater. You have to make a hole in the ground. You have to put pipe in it or something thereof. You have to measure it either manually with a tape or an electronic sensor, or thank goodness we have transducers to help us understand and help us log this information that we have. Well, there's one. Come on. Anyway, nobody cares about that. That's what I've done. So we have several varieties of transducers. You have vented and non-vented style transducers. Now, one of the easiest to understand is a vented transducer, right? So you have, basically all transducers are measuring is pressure. That's the only thing they're measuring. And they don't care where the pressure comes from. They measure all sorts of pressures. So basically it's a singular cell, as you can see in the, right there. It's a singular disk cell that registers pressure whether it's on one side or the other. And it causes that cell to flex one way or the other. And that cell flexes an electronic membrane that sends a signal to a data logger or to your logging instrumentation. And so that's all it's measuring. That pressure can come from changes in groundwater. That pressure can come from changes in lithostatic head. So all you're really measuring is differential change. Now, as scientists, as groundwater people, it's up to us to determine where differential change is coming from. So you can't just read it like you're reading a book straight off the page. You have to spend some time and understand why that sensor is performing the way it is. You also have to do QA/QC on your data to make sure that the data that you're seeing is not invalid data or data that doesn't truly match the reflection of your water level that you're actually monitoring. So a vented transducer, as you can see, measures atmospheric pressure on one side of the transducer and differential between the movement of the groundwater. So the water and anything below the membrane is pushing on the membrane. And it's open to atmosphere on the top. So being open to atmosphere ultimately corrects for the changes in barometric pressure above it. Because believe it or not, right here as we sit in this room, we have 14.7 pounds sitting on us right now, compressing us. That's what puts air in our blood. And so your transducer with a vent behind it automatically has 14 pounds mashing on this side of the load cell. When you have fluid rising, mashing on this side of the load cell. So any changes in barometric pressure above the sensor, which is also affecting the water, is normalized. So basically you're seeing just the effects of the water level on the load sensor as the water level changes in the well. Now a non-vented transducer, it's got a vacuum behind the load cell so that the effects of barometric pressure are not sensed by the cell. So it's a cumulative process. So you get barometric pressure changes in the groundwater, and any other type of pressure regimes that may be going on within your system. So all effects of pressure are materialized on a non-vented transducer. And in a vented transducer, the effects of barometric pressure change are neutralized. So that's how you start with the concept of whether you're going to reuse a vented transducer or a non-vented transducer. And there's variations in expenses and understanding that help you make that decision. Sometimes it's all expense driven, sometimes it's data driven, and that'll help you coalesce on a final decision. Before you buy a transducer, we're really tempted to do a one-shot fits all, right? These things are very expensive. I've seen a lot of hands raised up out there, and so you've all bought at least one of them. And it's painful when you start buying two or more. So you know the cost values are pretty high on these. And so before you buy your sensor, you need to understand what it is you're trying to monitor. Because one size does not fit all. One size does not fit all. If you look on this, go back. There we go. If you look at this particular chart, you notice that as your pressure ranges go up, your precision and resolution also change. And that's the resolution and the precision of your data set. So if you're really looking at something that has a small, narrow window of margin, you need to use a lower pressure transducer so that it captures more accurately the data. Because there is an offset in your data. No matter what you use, there's a measurable offset, whether it's in resolution or in accuracy. I'm not going to sit here and go through all the math, but it's 0.05% on accuracy and 0.005% on resolution. Those seems like really small numbers. There's so many behind the decimal point. But as you go up in pressure, that resolution can be quite large. Say a 500 PSI transducer that's full scale resolution, can be as much as 5.7 feet off in accuracy. So if you're measuring a really deep aquifer and you've got your transducer set in all the way to the bottom, then you can have an accuracy error of almost 6 foot, 5.5 foot of accuracy. Even though your resolution may be only a half a foot, your accuracy could potentially be off by almost 6 feet. So when you use these, you really need to be conscientious of the region and why you're using them. If they're strictly just for general data collection, you want to try to match your transducers to the fluctuations of your water well or your zone that you're monitoring and the amount of head that's over top of the transducer. So you don't want to put a 100 PSI transducer in a 500-foot well with 500 foot of water over top of it. It's liable to destroy the sensor. So you want to match your load cells or your PSI proportionally to the range in which you're going to be operating your units so that you maximize that full-scale potential. With non-vented transducers, you have to run a barometer. You can't strip atmospheric data out of it unless you run a barometer, either on-site or within 5 miles or so of the actual well or location that you're monitoring, because you have to strip out the barometric pressure data. And these things are cumulative, they're additive. So you have 0.005 or 0.05 accuracy on one transducer, and you've got the same accuracy in your barometric pressure transducer. So that error now is additive. So you may have a couple of foot of error in one, a half a foot in the other. Now you've got 2.5 foot of induced error that you have put in there in your own data set prior to any manipulation of the water. So you have to be conscientious of what instrumentation you're using, the accuracy that you need, what questions you're trying to answer, and where your instrumentation is located. As weather patterns move through, you'll see barometric pressure change ahead of your cold fronts, ahead of your warm fronts. And if your barometric pressure barometer is too far away, it'll reflect that ahead of your data. And so when you merge these two and strip out the data, you'll automatically induce errors in your data simply because your barometer was too far away from your transducer. So really it's best if you're going to be running non-vented transducers that you have your barometer at the same station, the same location you run your non-vented transducers. So some of the benefits of running an absolute or non-vented transducer is absolute pressure transducers. They automatically, you have to be compensated for barometric pressure change. We talked about that. And then you have to do post-correction of your data. But they are easier to deploy. You can deploy a non-vented transducer on a stainless steel cable, drop it down in a well, suspend it at the well cap, and basically your cost is the transducer. Whereas a gauged or vented transducer, they don't have to be compensated for barometric pressure because they're self-compensating because they're vented on the back. But the cabling can be more than the cost of the transducer. Cabling is very expensive and it's sensitive. It can be easily damaged. Rodents, they love that stuff. You can't imagine how many times rats have come out and eaten my transducer cable. You say, well, just bit the little of it. It only bit the conductor wire. But that cable is like $5,000 for one little run of cable. So you've got a $5,000 cable and a $5,000 transducer, and that starts adding up. But it gives us a really nice, clean data set. How many have ever had rodents eat their transducer cable? Well, there we go. So you can attest to those pesky dudes. Now we have several different kinds of transducer mechanisms. We have smart transducers that have built-in data loggers inside the units themselves that are self-contained battery, data, volatile memory, load cell, all within the logger itself. And then we have just sensors that, again, are just that load cell. And they send electrical signal up their cable to a data processor and a data logger. The downhole load cells aren't near as expensive as the combined smart units. But on the surface of a load cell, you have to have a system that's compatible and a system that's capable of reading this voltage that's coming out and logging that data, keeping track of that data. So you do have another component that you have to be conscientious of when you run strictly just downhole load cells or downhole level sensors. The downhole sensors, they come in 0 to 5 volts DC, 4 to 20 milliamp. That's a real popular style of transducer. SD1 or SDI12 or Modbus slave components that hook up to, some of y'all may have seen the OTT or Sutron display up here. Those will fit something like that. One of those kind of, well, as you see there, one of those SAT-link data loggers. I know that some districts use these SAT-link loggers to hook to the GOES network. I suspect there's at least one group in here that uses the GOES system. Anybody use the GOES network? No? The satellite network that the state provides? No? Okay. Anyway, it's available if you can work with the Texas Water Development Board. Sometimes they'll help set a mesonet that you can connect to satellite service with. Now, prior to deployment, you're tempted to just want to drop these things in the well and be done with them. But they're not that easy. They're a lot more sensitive to change and sensitive to damage. So prior to installing these, you really want to inspect them and clean them. They've got a little foil load cell in the bottom that if you poke it or punch it or it gets mud in it, it won't work. And especially if you dent it, it doesn't fluctuate. So you have no data or your data is very corrupted. So you have to be really careful, but you want to clean these things and make sure that you have a good battery life on them. If they're the self-contained units with the built-in batteries, you want to make sure that the battery life is going to be compatible to the duration in which you're going to be running these loggers in your instrumentation. As well as memory. The memory is really critical because depending on how many data points you're assigning and the speed at which you are collecting this data, it can easily overflow your onboard memory. Some have a function where it'll wrap around and basically erase the first part of your memory set, or data set. So you may go out there and have inadvertently had it logging every half a minute, and you think you've got 6 months worth of data on there, and you go out there and it's like, oh, I've got 12 minutes worth of data. So you got to be conscientious when you prepare your data set, prepare your programming, that you understand the amount of volatile memory you're going to use for each data set, and make sure that your transducer supports the time period and the amount of data that you're going to be collecting for your project. You want to do an open air test. How many have ever done an open air test on the transducer before they put it in? Anybody? I see a hand or two. If you haven't been, you need to start. How do you know the mechanics are working? On a vented transducer, it should read really close to zero. There should be some fluctuations in it. There should be some eddies in it, but it should be pretty close to zero. But if you haven't done an open air calibration before you put it in, you put it in the well, you turn it on, you fire it up, and whatever data you get is going to be what it is, no matter how inaccurate it might be. And you won't have any way of QA/QCing that information unless you've performed the test and then wrote the number down. Some of the transducers, not all of them, have a calibration for the weight of water. So not all water weighs the same, right? So some of this water is heavier than others. I don't know, I've only seen drilling mud that's lighter than water, but some of this water is heavier than others. So if you don't put the proper calibration, remember at the start of this, we said that all the transducer sees is pressure. That's all it sees. And the variations in the weight of your water will change the way in which the transducer sees that load. So you can have already an inaccuracy built in simply by the difference of the weight of the water in which you're measuring. So you make sure that you calculate your weight of the water and include it in your setup whenever you launch your transducers. Some of the companies provide water quality transducers along with their pressure transducer portion of the data logging. Has anybody ran any of the water quality transducers in conjunction with your water level transducers? Anybody? There's a taker. There's some really nice tools out there that read TDS, conductivity, temperature, a whole data suite, OD, whatever you want. They've got a transducer that you can incorporate with water level. But you got to calibrate them before you launch them. And then you got to come back regularly and recalibrate because they have a tendency to drift during deployment. If you don't calibrate before you launch it, all the data that you get is of no value. It's got to be calibrated against the standard. And again, recalibrated pretty regular, monthly or so. You got to come back and recalibrate them. But they give you phenomenal data. A lot can be said about the migration of contaminants simply by having a transducer in the well that monitors TDS, changes in water quality. You can see fronts moving through your data as water quality drifts from potentially fresher water to water of higher TDS. You can capture that in your downhole data loggers. If you've got a problem area where you believe that you're getting intrusion from somewhere or something's going on you can't quite figure out, you can deploy these data loggers that have the capacity to capture TDS and conductivity and log that over time and watch and see these variations in water quality coming in, especially like in a commingling situation or something like that. You can watch these variations in water quality through transducers that have this capacity. For vented transducers, you have the great benefit of having vented to the atmosphere, and so it takes care of all the fluctuations in the atmosphere, but it also deposits water vapor within the vent tube. As air rises and falls and heats and cools, tiny droplets of water vapor will condense in your vent tube. And if they make it down to your load cell, it short-circuit the load cell and gone is $5,400 worth of transducer. So you got to run a dissecant on the vent tube, and you have to have a large enough dissecant packet that's capable of consuming the moisture that's in the air for the duration of the time in which you're going to be operating your transducers. So you want to make sure that you keep your dissecants fresh and changed so that you don't ruin your pressure transducers. And I'm going to run out of time. I'm sorry. So collect static water levels prior to deploying your transducers, because if you don't catch the static level before you deploy it, it's not going to mean much whenever you're trying to do comparison across sites. If you have a whole network of transducers, you have to capture that and compare it back to relative elevation. That way you can do potentiometric surface maps of your groundwater. You have to measure your static level, and then you have to measure your measuring point to tie it back to elevation. And then you want to make sure that transducer is tied off and hooked pretty good, because it's really hard to fish those out of the well. Anybody ever lost one in a well? There's a taker. So now barometric pressure. I don't know if we have enough time to get through much of this, but this is the effect of barometric pressure, right? And you want to have a barometer on your site. And you want to be able to capture changes in precipitation and barometric pressure so that you can strip it out of your data. As you can see, this is off of a site that I did. One is an airport barometer, and the other is a on-site barometer. The red is the on-site barometer. And we had this site that caused tremendous problems because we were on vented transducers, but there was still fluctuations in the data that could not be counted for. And these aquifers, sometimes when you're dealing with semi-confined aquifers and confined aquifers, the water levels are susceptible to changes in barometric pressure just as much as your load cell was susceptible. So your load cell, the vented on your load cell just takes care of the actual barometric pressure change, but it does not take account for the changes of the aquifer movement from barometric pressure change. So you have to apply a correction coefficient to your data to strip out the effects of the barometric pressure change on the actual aquifer itself. It's called barometric efficiency of an aquifer. I'm not going to explain how to calculate it because I'm out of time, but it's basically water level divided by changes in barometric pressure gives you a correction coefficient. And this is what a correction coefficient looks like on a data set. You find the cleanest portion of your data set to get your offsets and apply a correction to your data set. And we'll go on past this because this is basically the actual mechanics of how to do it, but this is the effect of what it looks like on your data set. The blue line that's all jumbly is uncorrected water level on a transducer that is vented. The orange line is the corrected water level based upon the effects of barometric change on the actual aquifer itself. Now, the orange line looks a lot more like a pumping test and less like a bunch of squiggly lines. Now, it's important to collect your data, collect long streams of data before you pump, before or after, so that you can look at transient signals, because there are transient signals in your data. that have to be cleaned out before you process it. That is an actual off-site pumping from a well field that's a mile away in our data, and we had to strip it out, had to include it in the model. And that's what it actually looks like. And I confirmed this because I went to the well field and I asked the operator for their operational data set of when they were pumping, how many wells were pumping, how much they were pumping. And I was able to include it in my aquifer model. And that's why you record long-term data sets prior to and after your pumping test or your analysis. Oops. Go back there. So we were talking about, quit it. We were talking about earlier about damage in your data sets. You have to be able to recognize that damage within your data set. When you have information that doesn't belong there or things that don't make sense, sometimes it's a mechanical error in the actual instrument itself. So you have to be able to recognize damaged data sets and not just blindly incorporate them, or else you'll make some terrible errors in your calculations. And then you have to realize that there are hydrologic effects that also affect your data. Yeah. Whether it's confined or leaky or unconfined or commingling, that is all pressure, and all of that is registered within your transducer. So you have to be able to start stripping out that information, each piece at a time. It's not a simple process. It's not just record it and play it. You have to work and tease the data out of it. Again, this is a combined image of formation, temperature, and a pumping curve. And these are all scaled to the same scale. So temperature is one of the functions on a lot of your transducers, and it's always important to capture temperature so that you can determine if you have inflow from other regions while you're pumping. And it's right there. Any questions?
We have time for one question. Is there any questions from the audience? Not, again, everyone will be around for any additional questions that y'all may have. Thank you very much.
Thank you, ladies and gentlemen.